Okay, grades 11s and 12s. So we are just continuing on with solutions. So last week we kind of worked on terminology and solutions and kind of the basic idea of what a solution is. Today's lesson is going to be kind of on factors affecting whether something will form a solution, whether something will dissolve in something else. So you kind of pick your solute, you pick your solvent, and this is kind of the lesson as to whether or not they'll actually form a solution. If I put these two things together, like if I take 100 grams of, this solvent, and I add this solute, will it actually make a solution, or will it do something different? Okay, so let's go with this. So this, again, the main thing, what we're going to call this is factors affecting solubility. Okay? And really it's factors affecting if something will form a solution, aka dissolve. Will something dissolve or not? Okay? So here's an example of Kool-Aid where something will dissolve, where you've taken sugar, which is the solute, water is the solvent, and we've made a solution, which is Kool-Aid, okay? Because these two things are soluble. Now, other things aren't soluble, where you pick them together. So here, oil is the solute, so this would be oil, okay? And we're using that as the solute. And then we have water as the solvent. Okay? And these things are not soluble, they're not mixing together. Okay? These things aren't dissolvable. So we kind of have to figure out, well, how do you know whether this is going to happen or this is going to happen if things are going to be soluble together? Okay, so the key thing is to remember is that almost everything is soluble to a certain extent. Okay, it does seem surprising, but almost everything is dissolvable to a certain extent. So if you take a t-shirt and every time you wash it, a little bit of that fabric gets dissolved. And that's why t-shirts wear out over time. And the more you wash it, the harder it is on your clothing. Okay? But that's why your clothing is breaking down, is you're actually dissolving a little bit of it. When you have water running over dirt, okay, it starts dissolving some of the dirt and creates crevices, and that's what causes our creeks and rivers and lakes that we see. So everything is dissolvable or soluble to a certain extent. It's just some things are really not soluble, like oil and water, and other things are really soluble. Now, the degree at which compounds are soluble differs. So how easily some things dissolve than others. Now, there's really four main factors that contribute whether something is going to be able to be soluble in something or not. Okay, and it really comes down to a few of them, and I'm going to kind of highlight them. So one is temperature. Okay, what is the temperature of, mostly of the time, it's the solvent. If you're using hot water, you can dissolve more than, say, cold water. When you're talking about solids. Okay, particle size. So how big of the particles of the solute. Okay, so something like huge, like say sugar, or something smaller like water. The pressure the solution is under, and then the polarity. So we're going to kind of go through these four things, and that's what the lesson is on. So the first one is going to be the Celsius. It's important, and that's temperature. So temperature has a huge effect on whether or not something will be soluble. So the effect on temperature, on solubility, okay, is dependent on which state the solute is in. So whether you're using a gas, liquid, or a solid. Okay. Now, the general temperature rule, and these are the important ones that I've highlighted in red, is that solutes, so if say something like sugar and water, solid solutes dissolve more with increased temperature of solvent. An example, you can dissolve more sugar in hot water than in cold water, and that's why we do it when we make Jell-O. Okay, we want to dissolve so much sugar in Jell-O that we can't do it using cold water, you got to use hot water. So whenever you're going to take a solid and dissolve it into a liquid, if you want to dissolve a whole bunch, you want the temperature high. Okay? Now, if you're going to take two liquids and you're going to dissolve them together, it's different. Okay? Liquids are unaffected by temperature. So you can't dissolve any more ethanol in water if it's hot or if it's cold. Or you can't dissolve any more oil in water, whether it's hot or it's cold. Temperature doesn't affect the liquid into a liquid. Now, this is an interesting one because this is going to be the exact opposite of solids. Okay? When we look at gases, okay, gases decrease with temperature. So let me highlight that. Gases decrease with increased temperature. So you can dissolve more gas in cold solvent than warm. The exact opposite is solids. So an example, you can dissolve more CO2 in cold water than hot water. So if you have a really, really cold pop, it will stay fresh and fizzy for a lot longer because what a cold pop is really just CO2 dissolved in water. And if you have something warm, it will go flat a lot faster because you can't keep as much gases inside it. Now, this effect, so we're really only going to be talking about solids and gases because liquids are unaffected. So we're really going to kind of take a look at the solids and liquids. Now, the effect on temperature is really shown on what we call a solubility curve. Okay? And I'm going to show you these because this is going to be a big part of the lesson. Okay, I'm just trying to 90 degree. You just switch slides. Slide here. Okay, here we go. Here's a solubility curve. So what we see here is, let's take a look first at the axis. So whenever you see a graph, you should take a look at the axis. So this is temperature, and as you can see, it goes higher. The temperature increases along the x-axis, and then here, this is the solubility. So this is basically how much you can dissolve in 100 grams or 100 mils of water. So if we look at here, as you go up across the temperature, so let me just kind of take a look. Let's take a look at just one right now. Let's take a look at sodium chloride, okay? And I'm going to highlight this. So when we look at sodium chloride line, what it's showing is that at 0 degrees Celsius, you can dissolve about 35 grams of salt in water that's 0 degrees Celsius. But then if you increase that water temperature to say, if we increase that to say 90 degrees Celsius and we go all the way across, it looks like we can get to about 38 or 39 grams. Okay? So what that's showing you is that as you increase the temperature, as I go from left all the way to right, okay, generally I can dissolve more. And if you look at all of these trends, like if you look at potassium chlorate, okay, increases, you can dissolve more as the temperature goes up. I can dissolve more. Okay? I can dissolve more. I can dissolve more. I can dissolve more and more. The only one that's really, really odd in this case is this one, which I'm going to highlight in blue. Okay? It actually shows that as you increase in temperature, the solubility goes down. But that's the only odd one. Everyone else, so if you look at this, the general trend for solids, okay, and this is again for solids, is that as you increase the temperature, you can dissolve more. Now let's take a look at for gases, because gases is the exact opposite. Let's take a look at, say, oxygen. So I'm going to highlight oxygen's curve. So oxygen is O2 here. And it's the same thing. We got temperature going up on the x-axis and the number of grams or milligrams you can dissolve on the y-axis. And you can see that at really, really cold temperatures, like 0 degrees, you can get a lot of oxygen dissolved. But as I increase in my temperature and as I go from left to right, you can see the amount of oxygen I can dissolve decreases. And that's true for all gases. Okay? So as you increase the temperature, the amount of gas that you can dissolve in the water decreases. So the opposite curves for solids and liquids. Okay, so we're just going to skip over these questions because I will probably add some of these to the learning check. Okay, so this is just a quick question here. So using your understanding of solubility, explain the potential reasons for the following. So these sugar crystals, you may have seen these before. Well, how we make these. Okay? So if you want to try and think before you kind of read this blurb, of, well, how would we possibly make these sugar crystals? Well, if we were in class, we would actually make them. And how you simply do it is that you heat up the water to really, really warm temperature. Okay? And then you supersaturate it with sugar. So I basically dissolve a tremendous amount of sugar in that hot boiling water. Okay? Now, as the water cools, I can't dissolve as much sugar because I can dissolve more sugar at, say, 100 degrees Celsius than I can at 50 degrees. So as that water cools, the sugar comes out of being dissolved and becomes a solid again. And that's what you're seeing here. So how you make these is basically you boil some water. Okay? You have to saturate that water. You have to put as much sugar as you possibly can into that water. Okay? Then you basically put a stick inside that water with a little bit of sugar already on the stick. And then as that water cools, this crystal will grow. Okay? And it'll grow basically on that stick. And that's how crystals are made, or sugar crystals. Now, the other thing is you may have seen this at Erio. So this happens every once in a while where a whole bunch of dead fish all pop up on shore. And the reason for this is it follows a heat wave. If it gets really, really warm, remember that less oxygen can dissolve in the water. So if it was really, really cold water, okay, lots of oxygen can dissolve, lots of oxygen for the fish, because fish need oxygen just like we do. But as the water warms up, less oxygen is able to be maintained in there. So you're going to get oxygen basically coming out of the water and going into gas. And as that happens, the fish start suffocating and dying, and they end up on the shore. Okay, so we just did temperature. The next thing is particle size. So this is really short and simple. Basically, the smaller your particle, the more you can dissolve. So a really, really small particle like methanol, you can dissolve as much as you want into it. It'll never become saturated. Okay? If you get a little bit of a bigger molecule, you can't dissolve as much. Okay, you can only do 9 grams for every 100 mils of water. And even as you get bigger, so now we even have a bigger molecule, now I can dissolve even less. So the general idea is the smaller the molecule, the more you can dissolve. And there's not much more to say on that. Okay. Here, this is how they would normally state it. So butanol, 9 grams per 100 mils at 25 degrees Celsius. And they would also usually include like 100 kilopascals, okay, which is indicating the pressure. Now, the next one is pressure. Now, pressure is basically how many molecules are exerting a force down on you. This is what pressure is. It's basically the weight of molecules above you pushing down. Now, changes in pressure have the most effect on the solubility of a gas into a liquid. So if we're going to put a gas into a liquid, that's where pressure is going to have a big impact. It doesn't have as big of an impact if you're going to take a solid into a liquid or a liquid into a liquid. They're almost unaffected by pressure. But if you want to try and get a gas into a liquid, pressure is usually the best way to do it. So the solubility of a gas is directly proportional to the pressure above the liquid. And what that means is that if I double the pressure, I can double the amount of gas that I get in there. If I half the pressure, I can only dissolve half the amount of gas. Okay, so if you kind of look here, if I decrease this by 50%, okay, so going from this one over to this one, I've decreased the volume by 50%, which increases the pressure by 50%. I can get now 50% more molecules inside the liquid. Go back 2 slides here. Now, if they don't indicate anything, if they don't... Okay. So because pressure and temperature can have the biggest major effect on solubility, solubility is often stated with temperature and pressure. They usually don't state the size of the particle when they're talking about solubility, but they'll usually state both of these because they have such a big effect on solubility. Now, if they don't state it, if they don't say, oh, it can dissolve, like if I go anything, they just say 25 mils, then you can assume that it's SATP. And what SATP means, standard ambient temperature and pressure. And as a chemist, you should know that our standard temperature is 25 degrees Celsius, and our standard pressure is 100 kilopascals. Okay. So if we were in class, we talk about the bends and what causes that. I may give you a lesson tomorrow about what causes the bends. Now, the last thing we have to talk about is the last indicator of whether something will dissolve. So we talked about temperature, we talked about size of particle, we talked about pressure. The last one is polarity. Okay. So all substances are considered either polar, and this is just a recap. If you're polar, you contain partial charges or full charges on distinct ends, like water or an ionic compound. So this is a polar compound here because I have a partial negative here, partial positive, considered a polar compound. Now, a nonpolar compound is where the molecules have no partial charges, so they don't even have dipoles, or they have the same partial charges all around the molecule, like here. Here there's partial charges, but it's partial negative here, 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 and here, so it's a nonpolar molecule. So every single molecule out there can be considered either polar or nonpolar, and ionics are the ultimate polar compound. Now, here's the idea. Polar molecules can dissolve other polar molecules easily, but nonpolar molecules can dissolve other nonpolar molecules easily. However, this is the big difference. Polar and nonpolar do not mix easily. So you can't take two different kinds of molecules, like a polar and nonpolar, and mix them together. It just doesn't work, or it doesn't work well. So an example of that would be like CO2 and water. They don't mix well together, or oil and water mix well together. Okay. So there's this general rule which we call like dissolves like, and that's the idea that polars dissolve other polars, like dissolves like, or nonpolars dissolve other nonpolars. And it's just a general term that we use in chemistry called dissolves like. Now, why? Why are they having an effect on polarity? Well, polar substances only dissolve other polar substances in ionics. And why do nonpolar substances only dissolve other nonpolar substances? Well, if you remember, polar substances in ionics contain charges. either partial positives or partial negatives, or in an ionic, a pure positive or a pure negative. So when things dissolve, okay, they basically have these charges interact. These charges interact and allow them to dissolve. So something like the charges on water interact with the charges on chlorine or the charges on sodium, and that causes dissolving. Now, nonpolar substances that lack charges and can't interact with the polar charges. They can only interact with other molecules that lack charges or other nonpolars. So that's why polar compounds can only dissolve polar and nonpolar can only dissolve nonpolar. So here's just an example of water dissolving an ionic compound. And what really happens there is the water molecules basically just start surrounding each individual atom. So that atom of sodium is surrounded by water, this chlorine is surrounded by water, and they're kept apart. And if they're kept apart from bonding, that's what dissolving looks like. Okay. So water is considered the universal solvent because it can dissolve so many different solutes. It can dissolve almost any ionic compound because it has charges and water has charges by forming dipole ion bonds, and any polar substance by forming dipole-dipole bonds. Okay. So the three main reasons it is such a good solvent: it's a small molecule, it's polar, okay, and it can form hydrogen bonds, which is a special type of dipole-dipole. Okay. So what can't dissolve? Nonpolar substances, that's what water can't dissolve. It's anything that's nonpolar, like CO2, like oils, like gasoline, anything that's nonpolar and doesn't contain charges. Now, there is some things that can dissolve nonpolar things, like acetone. So I showed you an example when we were in class of acetone dissolving styrofoam. Now, anything that is nonpolar is really dangerous because the only other thing or something else that's also nonpolar is our skin. So if you get something that's nonpolar, like acetone or like gasoline, on your hands, it actually dissolves in. So that's why if you get gasoline on your hands, it's very difficult to get the smell out. And the reason for that is the gasoline has actually entered your skin. It's actually not on the surface anymore, it dissolved inside. So you have to wait till those layers of skin basically fall off. Or if you do really, really hard scrubbing, you'll actually be scrubbing those layers off. And that's why things like acetone or paint thinner or gasoline, it's very difficult to get smell out of your hands. And it's also very dangerous to be using without gloves. So it's a very dangerous thing to be getting nonpolar compounds like gasoline or paint thinner or kerosene or acetone on your hands because, again, it dissolves into your skin. All right, thanks, guys.